today's lecture is about soft clustering methods. What I want to teach you today is the basic idea of soft clustering. So what is soft clustering compared to hard clustering? And then we will spend some time on discussing a very simple but powerful soft clustering algorithm, which turns out to have a nice interpretation as fitting a probabilistic model. This probabilistic model is known as Gaussian mixture model. And using this interpretation, for example, we can analyze this algorithm or even choose parameters for these algorithms like the number of clusters or stopping conditions. So this is an iterative algorithm like k-means, and we need to specify a stopping criterion, so when to stop the iterations. And one stopping criterion can be derived or can be motivated by the probabilistic interpretation of the algorithm. But first things first, so what are three components of machine learning? Yes, I want to see 10 answers with the right answer. Yes, good. So this is my main message in the whole course. Machine learning combines three components: data, a model, and the loss. So maybe the main component is data, and it's up to us what we define as data points. So a data set is just a set of data points of entities of a similar type. So we can say a data point is an image, or we can say a data point is a small part of an image. So we can say one image is a whole data set. So the data set underlying this image here is just a set of all these rectangular patches. So I can cut one image into several patches, and each patch is a single data point. So the whole image here, this is a snapshot from a lovely ski route from Vuussaari to Talusaari for the experts among you. So this one snapshot is one data set, and this consists of several data points. One data point is one such patch. And as mentioned several times in the course, a data point is characterized by properties, and we distinguish between two types of properties. One type of properties are features. This is something which can be computed or determined or measured easily in an automated fashion, whereas other properties are called labels, and they are not so easy or typically involve their determination involves human work. So an expert needs to look at the image. Is it a cat or a dog? In this example, we use two features for a data point. So remember, a data point is one patch, one small patch of that image, and we compute two features, or I have computed two features. I think this was done in a Python notebook. And I compute the average red component and the average green component of all pixels in that patch. So I get then two numbers, a redness index, the average red component. For this image, it is around 150. And for this image, I get an average green component of 100. So each data point here is characterized by two features. Yeah, and I got some questions regarding the course project, because you are essentially required to consider two different models. And if you use two different sets of features, then these are already two different models, even if you use the same machine learning method. So let's say, for example, here, you consider one machine learning method that uses linear regression using the redness and the greenness of a patch. So this is one model. And then another model would be linear regression using the redness and the blueness. So this is a different set of features. As soon as you use two different sets of features, even when you use the same type of model, like linear predictor maps, they are different models, strictly speaking. And then you fulfill the requirement for the student project, which is to test at least two different models, compare them based on the validation set error, and then choose the better one. Okay. So, but today we don't want to learn a predictor. So in these student projects, you are asked to learn a predictor of some label. So what could be a label here for a data point? I have now explained two features. Could you think about a label? So what could be a quantity of interest of each of these patches? What could we be interested in to know about a certain sub-region of the image? Yeah, for example, does it contain a relevant part of an object, like of the snow cat? Or does it contain snow? So is it like a background or foreground part of the image? So this would be labels. But today we don't assume that we know that anybody labels these patches. So today we talk about methods that don't need the specification for any of these patches. Is it a foreground or not? Yeah, there's another suggestion for a label. The label could be the time that the picture is taken. Yes, but then the label would be the same for all data points, because a data point is a subset, is a sub-region of the image. And if we use as a label the time at which this image has been taken, then this would be the same for all data points. Yeah, so a label could be, for example, does that patch contain mostly pixels that correspond to the snow cat, snow groomer? Okay, and today we talk about soft clustering methods, which are a fancier version of hard clustering methods, which we talked about last lecture. So in hard clustering, we can group all these data points. So remember, each data point here is one image patch, and we want to group them into, let's say, two clusters. So clustering methods group a data set into subsets, which we call clusters, such that within a cluster, the data points are more near to each other. And if we do this, if we use k-means that we talked about last lecture, we get this. So we get for each data point, we know if it belongs to cluster 1 or to cluster 2. And then what I did now, I just left in the image all patches which belong to the same cluster, let's say cluster 1, and I zeroed out all patches that belong to the other cluster. So, and it seems that this cluster here that I got is the snow cluster, so to say, or the background. It doesn't contain much of the snow cat. Yeah, there's one question a bit off topic. After the quiz deadline, are the correct answers available so I can learn from my mistakes? Yes, you can click review on the quiz, and then in the end of today's lecture, I can also answer questions, specific questions to the last round 4 quiz. But let's now continue with soft clustering. So let's say we don't want this hard clustering. This hard clustering is a bit rough. So there might be some patches which are on the boundary between the two clusters. So this here, for example, these red parts, they don't really belong to the snow cluster, but still are assigned to the snow cluster. At some point, hard clustering must draw the line, so to say. So the hard clustering or k-means draws a line somewhere, tuck, and everything on this side is cluster 1, everything on that side is cluster 2, period. And this is not so useful when you have data points that are near the boundary, because it would be nice to know which data points are somewhat mixed case or on the boundary, and which data points are very kind of strictly inside the cluster, one cluster. And this we can do with soft clustering. So in soft clustering, we don't get we don't assign a data point or a patch to a single cluster, to one and only one cluster, but we assign each data point to several clusters, and we specify a degree of belonging by which a data point belongs to a cluster. So what I did here is I used soft clustering for each patch, and then depending on the degree of belonging to cluster 1, I changed the brightness level. So I made the data points which belong very much to cluster 1, I left the brightness, and then for data points that do not belong so much to cluster 1, I reduced the brightness level. So I made it darker. And you see these red parts here of the snowcat are darker, but also you see that there's no really patch that is completely black. So each patch belongs to some degree also to this cluster 1, which is the snow cluster. But I see more smoothly the transition between cluster 1 and cluster 2. And this might be nice also visually to use soft clustering. So again, this is what you can do with k-means, with hard clustering. Each data point, which is a patch here, a sub-region of the image, is assigned to one cluster and only one cluster. So every patch that is shown is assigned to cluster 1, and every patch that is not assigned to cluster 1 is assigned to cluster 2 and therefore not shown. In contrast, in soft clustering, each patch is assigned to cluster 1 with a certain degree of belonging. And here, every data point is assigned to cluster 1, but with different degrees of belonging. If the degree of belonging is high, and we will use a normalized range of values for the degree of belonging from 0 to 1. So if the degree of belonging of this data point is 1, then we make it very bright. And if we then look at, for example, this data point here, if the degree of belonging is low, close to 0, then we make it darker, much darker. So this is what we can do with soft clustering. So let me formalize this setup. Again, we have a bunch of data points. So a data set is a bunch of data points. In our case, each data point here corresponds to one patch, image patch, a small subset of the image. And each patch is characterized by a feature vector. We used 2 features in the example before, the redness and the greenness. And we also have a label vector. So formally, we still have labels, but we use methods that don't need to know this label vector for any data point. But formally, they are still there, but they are unknown. So we don't know the label for any data point. But formally, we can define labels. So we can say the ith data point, or each data point, which is a certain patch, image patch, is characterized by a bunch of labels. So we have one label value for each cluster. We have, again, a certain given number of clusters. K is the number of clusters we want to cluster that data set into. This is similar to k-means. Also in k-means, we need to specify the number of clusters. Also here, this is given. Somebody gave us the number k, might be 2 or 3. So for each cluster, potential cluster, so this is a typo here. This should be, of course, y. Need to correct that. We have a degree of belonging, and this y1 I is the degree of data point I belonging to cluster 1, and yki is the degree of data point I belonging to cluster k. Okay. So in principle, we can freely define the value range, but it turns out to be useful or a good idea to set the value range of these degrees of belonging between 0 and 1. And this can be any number between 0 and 1. For example, the degree of belonging could be 0.33. This would be somewhat a boundary case. So exactly a boundary case would be when the degree of belonging to a certain cluster, for 2 clusters, for example, would be 1/2. So if this would be 0.5, then this data point would belong to each of the 2 clusters with the same degree of belonging. This would exactly be a boundary point. Where do we have the eraser here? So this degree of belonging can be any number between 0 and 1. And we will interpret this degree of belonging as a probability. This might seem weird at first sight. Why do we now need to bring in probability theory? But it turns out to be useful. So bear with me and just trust me on this. It's a good idea to define, this is now just a definition, we require this. We define the labels such that the sum over all degrees of belonging for a certain data point, so this I, this data point index is fixed here. And if we sum over all clusters, then the sum of degrees of belonging is 1. And what we express with this requirement is that the ith data point must belong to one of the k clusters. So even if it belongs only with 50% to cluster 1 and 50% to cluster 2, but it must with 100% belong to any of the k clusters. So this is something like a law of total probability. We can interpret this requirement as a law of total probability. So enforcing this summation constraint allows us to interpret these numbers as probabilities. In particular, we interpret YCI as the probability that the ith data point belongs to cluster C. And then what a soft clustering algorithm or soft clustering method does, it reads in all the feature vectors. So it reads in the feature vectors of all data points. These are only feature vectors. It doesn't need any labels. And it outputs a prediction or predicted degrees of belonging. So this output is Y hat. This output is Y hat, and this is in typical not the same. So this is typically different from the true underlying degree of belonging. So remember, we assume that we have some true degrees of belonging, but we don't know them. What the soft clustering method gives us is some prediction or some guess for the degrees of belonging, but they might be different from the true degree of belonging. So how do we represent the cluster? That's basically the main design choice for each clustering algorithm. So different clustering algorithms use different forms or different choices for representing clusters. Does anybody remember how k-means represents clusters? So how did we represent the cluster in k-means? As perfect squares, yes. And how did we parameterize these squares? So how did we describe where they are, the squares? Also, the name already indicates it, k-means. So how do we represent clusters in k-means? By each cluster in k-means is characterized by one representative vector, which is called the mean vector. Exactly. That's why k-means is called k-means. So in k-means, we represent the cluster by a certain prototype feature vector, or we call it cluster mean. And then we assign to this cluster all data points which are nearer to this cluster mean than to the others. And now we extend this, we make it a bit more flexible, this representation. We not only use cluster means, but we also define the shape of the cluster. In particular, we also use a covariance matrix to allow for non-isotropic cluster shapes. So they are now they now have the form of ellipses. In k-means, these ellipses were perfectly symmetric. So they were always the typical cluster shape in k-means are balls, so to say, which look the same in all directions. Here we have some anisotropic behavior. So the extent of the cluster is different in different dimensions. So here it's a long, but here in this direction, it's a very narrow cluster. And we can represent these shapes by covariance matrices. In particular, the clustering algorithm that I will present to you today uses a Gaussian distribution to represent the cluster. So this might sound now very weird. Why do we represent a cluster by a Gaussian distribution, by a probability distribution? But it turns out that this is the right mathematical tool, or this is a very suitable mathematical tool to represent the cluster. Why? Because we can then say for each data point, for any given data point. So let's say a new data point comes in. I observe a new image patch. I compute the redness, greenness features, and then I have a new data point here. Zack. So there's a new data point. Let's call this the ith data point, or the feature vector of the ith data point. And then I can say, what is the degree of belonging of this data point to this cluster? I can quantify this degree of belonging just by inserting the feature vector here in the formula for the distribution. So I insert here xi, the ith feature vector, minus the mean vector of the of the cluster. And then here I evaluate this quadratic form and I get a number. So this number is the value of the distribution evaluated at this new data point. And this distribution value, or probability density value, more precisely, satisfies all the requirements that I need from a mathematical tool that can be interpreted as a degree of belonging. So just bear with me. It's a good idea. It's a useful idea to represent the cluster by a whole probability distribution, in particular by a Gaussian distribution. And by the way, if we restrict ourselves only to Gaussian distributions, then this is equivalent to representing a cluster by a mean vector and a covariance matrix. As you might have heard in your first probability courses at university, a Gaussian distribution is fully specified by the mean vector and the covariance matrix. So if you know that a distribution is a Gaussian distribution, then you know everything about this distribution as soon as you know the mean vector and the covariance matrix. And that's why I started with saying, let's represent a cluster by a mean vector and the covariance matrix, because this is exactly what we need to specify a Gaussian distribution. Okay, so this is maybe the main mental challenge to understand the clustering algorithm, in particular to interpret the clustering algorithm. I will introduce in a second. The underlying idea is to represent the cluster by a Gaussian distribution. Okay, so once we buy this, so once we accept that, okay, let's represent the cluster by a Gaussian distribution. The next question then is, but what's the right choice? What's a good choice for the mean vector mu and the covariance matrix sigma? Well, what we can do, we can fit this Gaussian distribution to the data points we have. And this turns out to be equivalent to minimize a cluster spread. So similar to k-means, we can define a cluster spread, but the cluster spread is now defined in a different norm. So in k-means, we used the squared Euclidean norm. So in k-means, we used here the identity matrix instead of the inverse of the covariance matrix. And what, yes, so instead of this squared Euclidean norm, now we define the cluster spread by measuring distances using this this quadratic form involving the covariance matrix. And this has the effect to measure distances different in this dimension than in this dimension. And using this different distance measure, so this quadratic form, instead of using here the identity matrix in the middle, allows to make the shape of the cluster to be non-isotropic or anisotropic. So to make it kind of squeeze out in one dimension. This can be done because of the covariance matrix here, because we have this covariance matrix. Okay, and this formula here, so the cluster spread is the weighted distance, because we weight each data point by the degree of belonging. So this is the degree of the ith data point belonging to the class, to the first cluster, belongs to the first cluster. So we weight each data point by this degree of belonging. If a data point doesn't belong at all to this cluster one, then it doesn't contribute to the cluster spread. So let's say we have here another data point, which is, let's call this index the 10th data point. Let's say we get in a new data point, the 10th data point, and the current prediction for the degree of belonging of this data point to cluster one is 0. Then this data point will have no contribution in this cluster spread, which makes sense. It doesn't belong, currently we think it doesn't belong at all to cluster one. Therefore, it's not relevant to measure the distance of the cluster mean of cluster one to this data point, because it doesn't belong to this cluster. Okay, so we can define a cluster spread again. And yeah, then what we do, like we did in k-means, we minimize the cluster spread. We want to minimize the cluster spread, and it can be shown that this is achieved. So the cluster spread is minimized by choosing the mean vector of the cth cluster as the average. So this here is the average of the weighted average of all data points. So we weight each data point by the degree of the data point belonging to cluster 1. Okay, so this here should be C. I have to correct this also, and this should also be C. So this formula applied to all clusters. For all cluster index C equal 1 to cluster index C equal K. Okay, so these cluster means and covariance matrices are chosen to minimize the cluster spread. So let me illustrate this here in the picture. Again, the main challenge, I think, for this understanding the soft clustering algorithm is to believe or to buy that we represent clusters by Gaussian probability distributions. Once you get used to this, the algorithm makes very much sense. So if we represent the cluster by a Gaussian distribution, which is characterized by a certain mean vector and the covariance matrix, well, it seems supernatural to choose this mean vector and covariance matrix such that the spread around the mean here is minimized. And this is what we do in the update equations for the cluster mean and cluster covariance matrix for each cluster. So we minimize the spread for cluster 1, and then we choose the parameters of cluster 2 to minimize the spread of cluster 2. And these updates, which minimize the cluster spreads, are summarized here again. So given the current degrees of belonging or soft cluster assignments, we can evaluate these formulas and get new cluster means and new cluster covariance matrices. Okay, what is the problem in practice? Why? So remember, the clustering algorithm reads in as input only the feature vectors xi. So can we evaluate the first step here just by using the input? The input are the feature vectors. So this here is the input. This is given to the algorithm. What about this y hat? Do we know the degrees of belonging right from the beginning? No, we don't know. So how can we get the degrees of belonging? Well, assume now we know the cluster parameters. So assume we know the cluster means. So we know the cluster means. So this would be mu1. And the covariance matrix for cluster 1, sigma 1. And we know also this mean vector for cluster 2 and also the covariance for cluster 2. If we would know those parameters of the clusters, what we could do, well, we could calculate the probability if we assume that the degree of belonging is the probability that so we interpret this as the probability that the ith data point belongs to cluster C. Belongs to the cluster C. Okay, and we can then evaluate this probability by using our assumption that if a data point belongs to cluster 1, it is distributed like a Gaussian with mean vector mu1 and covariance matrix sigma 1. And this is exactly what is here. But this is the probability distribution of the feature vector given the fact that it belongs to the Cth cluster. But I'm interested in the other way. I'm interested in the probability that the ith data point belongs to the Cth cluster. And for this, I need to normalize by the sum over all probabilities that a data point belongs to a certain cluster. So this is what is shown here is essentially a Bayes rule. So this formula here for the degrees of belonging is the Bayes rule. So you can understand this formula by basic rules of probability. So once you identify these degrees of belonging, so assume that these degrees of belonging are this probability, you can derive this formula. Otherwise, if you do not want to subscribe to probability theory, you just have to believe me that this choice for the degrees of belonging makes perfect sense. It's a good choice. But as soon as you interpret these degrees of belonging as the probability that the ith data point belongs to the Cth cluster, then what you see here is just a basic computation of probabilities, or conditional probabilities, more specifically. Okay, I will not go into further detail because for this course, it's sufficient if you understand the basic outline and the basic kind of structure of the soft clustering algorithm. However, I want to point out that there's a strong and very useful probabilistic interpretation behind this clustering algorithm, which I will now present to you. And this interpretation is based on identifying these degrees of belonging with probabilities. But you don't need to do this. So this is just a convention. This is one way to look at the soft clustering algorithm. Okay, but now, so now we have this formula. Now we have this formula that allows us to compute the degrees of belonging. But what is the problem here now? This formula requires the cluster means and the cluster covariance matrices. On the other hand, to compute the cluster means and covariance matrices, we need the degrees of belonging. So this is again a chicken egg problem. We would need the degrees of belonging to compute the cluster mean and cluster covariance matrix. But to get the degrees of belonging, we would need the cluster means and the covariance matrices. So how do we break this dilemma? How do we escape this dilemma or self-reference? Randomize? No, I'm not sure about that randomization. But whenever you have two sets of equation which refer to the other, so or you have two sets of equation which refer so mutually to the quantities involved in the equation. So here we have an update equation that updates the mean and the covariance given the degrees of belonging. And here we have an update equation that updates the degree of belonging given the the cluster means and cluster covariance matrix. So whenever you have such self-referring update equations, there's a nice trick or a very powerful and widely applicable algorithmic recipe. So how do you iterate these equations? Yeah, solving the system of equation, but how do you solve the system of equation? So the system of equation looks like this. So we have one variable, let's call it A, that is f, some function, some update function, b. B is the other variable. And then we have another equation which says b, the other variable, should be g of A. Yeah, there's one suggestion now. We should calculate the mean vector and put it into sigma. Yes, yes, sure. Once we have the mean vector, we can use it to compute the covariance matrix. But even for this covariance matrix, we also need then the degrees of belonging. So where do we get an estimate for the degrees of belonging? We could use this equation, but for this, we need already an estimate for the mean vectors and the covariance matrices. Yes, we know the number of clusters, but we don't know the mean vectors and covariance matrix from the beginning. Exactly, very good. So it seems there's one mathematician in the audience. We start with an educated guess or initialization, and then we iterate. So we start with some initial choice, for example, a random choice for the cluster means, covariance matrices, and effective cluster size. And then we start. Since we have an initial choice for the cluster means and covariance matrix and this effective size, we can evaluate this update and get a better guess, or we get a first guess for the degrees of belonging. As soon as we have a guess for the degrees of belonging, we can insert this into the updates for the cluster means and cluster covariance matrix. As soon as we get a new estimate for the cluster means and cluster covariance matrix, we go back to the update for the degrees of belonging. Once we have a new guess for the degrees of belonging, I guess you get the hang of it. So we have again this iterative structure. We update the cluster assignments or degrees of belonging for given cluster means and covariance matrix, and then we use this to update the cluster means and covariance matrices. And we iterate those two updates until some convergence criterion is met. So here's the simple soft clustering algorithm in written form. The input, input also, I forgot here. Input is, of course, the data set, the feature vectors of the data set. So the input is the feature vectors of all m data points, but we do not require the degrees of belonging because this is what we want to find out in the clustering method. So we only take the feature vectors as the input, and we also need as input the initial guesses or educated guesses, as one of you called it, for the cluster means, the cluster covariance matrix, and the effective size of the clusters. Then we start iterating. First, compute a new guess for the soft cluster assignments or degrees of belonging. Using these new degrees of belonging, we update the cluster parameters and so on and so forth. Yes, there's one comment or question. Is it possible to start the other way around, to initialize the degrees of belonging and then do the first update on the cluster parameters? Yes, that's possible. It's a matter of taste, I would say, how to start. So if we, in this diagram, if we start here, if you start the first iteration here, or as shown here with the update the cluster assignment. Okay, because typically you need many iterations, like 10 or 50. And it doesn't then in the end really matter where you kicked off the iterations, here or here. Okay, yeah, just the intuition, the cluster shapes, as I said, in contrast to k-means, the cluster shapes are ellipses. So they are not balls anymore, which are symmetric or have the same, look the same in all directions, but they are squeezed and stretched in different dimensions here. So these are ellipses. However, they are still ellipses. So what we still cannot do is get clusters that look like this, that show like this. So where here I showed you last time data points that represent images of road markings. So each marker here is one image of a road marking. And then I used some clustering algorithm to group it into two groups, one bulk group and then a few outliers. And such a clustering we cannot do with the soft clustering algorithm today. That's not possible because this would mean that one cluster here would fully enclose the second cluster, and this is impossible for k-means. So for the soft clustering algorithm, which delivers such connected ellipses, intuitively speaking, as their clusters. Okay, but we will then here in the next lecture, next week, Monday, I will talk about connectivity-based clustering algorithms, and these clustering algorithms can get such a clustering. So they can find a cluster structure that looks like this. So concentric rings, for example. Yeah. Now that we have defined the soft clustering algorithm as iterations between the cluster assignment update step and the cluster parameter step, the question then arises, of course, when to stop. When should we stop? And to define a stopping criterion or to diagnose when to stop, it's useful to define the clustering error, which I've shown here. And this clustering error makes perfect sense in a probabilistic interpretation because it is the negative logarithm of the probability to actually observe the data points under a Gaussian mixture model. So what we use in this soft clustering algorithm, again, we represent clusters by Gaussian distributions, and this collection of k Gaussian distributions is called a Gaussian mixture model. And a Gaussian mixture model is just one specific one way to represent a probability distribution, and then we can say what is the actual probability to observe the data points that we observe, and this probability should be large, because if this probability would be small, let's say the probability to actually observe the data points would be 10 to the power of minus 20, then this would say that our model is not good, is not a good fit to the data set. So what we typically want to do is we want to find a probabilistic model such that the probability of actually observing the data under this model is as large as possible. And this is called maximum likelihood, the maximum likelihood principle. I will not go into any more details about this. There are beautiful courses by the math department about probabilistic modeling and maximum likelihood estimation. I just want to point out that the soft clustering error here is just the negative logarithm of this likelihood or the probability of observing the data. And then it makes sense to minimize this negative logarithm, because minimizing the negative logarithm means maximizing the probability of actually observing the data. So what the soft clustering algorithm does, it turns out, it does monotonically decreasing this soft clustering error. Or when you translate it into probabilities, the soft clustering algorithm tries to find a probabilistic model such that the data that you observe is very probable, or is very likely under that probabilistic model. Okay, but once you evaluate, since we can evaluate the soft clustering error in each iteration, we can then decide to stop iterating when the progress or the reduction of the soft clustering error is very small or falls below a certain threshold. So you typically specify a threshold, epsilon, like relative, like say the reduction is less than 1% compared to the last iteration. And then you stop iterating. So we can get a stopping criterion from this view as a viewing the soft clustering algorithm as an iterative minimizing algorithm for the soft clustering error. Yes, and this is very similar. So this is structurally very similar to k-means. Remember, in k-means, we also could define a clustering error as an objective function that k-means tries to minimize. And similar to k-means, also here, the problem is that this soft clustering error is highly non-convex as a function of the cluster parameters. So the cluster parameters, again, are the cluster means, the cluster covariance matrices, and the effective cluster sizes. And what we do in our soft clustering algorithm, we move around this axis here and try to find the clustering characterized by means, covariance matrix, and so on, that has a smallest possible soft clustering error. However, it depends heavily on the initialization. So if we initialize, if our first educated guess is here, then we run the soft clustering iterations, then we might up in this optimal clustering. However, if we initialize here, we are unlucky, then we end up here. And this is a local optimum. So the soft clustering algorithm is also prone to ending up in local optima. So to deliver a Gaussian mixture model or a soft clustering that is not optimal in the sense of having minimum soft clustering error. So what did we do for k-means to avoid the problem, or to cure the problem, or the risk of getting trapped into a local optimum? What is the idea? Very good. Yeah, we run the algorithm several times with different initialization. For example, each time we run the algorithm, we choose randomly a new initialization. We start here, then we start a new run starting here with a new initialization, then another initialization here, and then we choose then in the end those run or those repetition which ended up in the smallest, which delivered the smallest soft clustering error. This is exactly the same procedure as we did for k-means clustering. Yeah. Then again, another question is how to choose this number of cluster. Remember, this soft clustering algorithm requires the number of clusters as an input. Where do I have it? Did I write it? I also forgot it. I need to edit here. So also the number of cluster k is an input. For example, k equal 2 if you want to do a background foreground segmentation for images, for example. But how do you choose it in general when the application doesn't suggest a good choice or a natural choice? So what you can do is, again, you try out different values for k and then look at the behavior of the soft clustering error. So typically, when you start with a small number of clusters, you get a fast decrease in the soft clustering error, and at some point it then flattens out. So it doesn't really help much using more clusters after this elbow, and it then seems reasonable to choose this elbow. So to choose as number of clusters the value after which the decrease in the soft clustering error slows down. However, the problem with this elbow method, and this is also a problem of the elbow method for k-means, that sometimes for some data sets you don't have such an elbow. So the shape of this curve depends heavily on the data set you have, and for some data sets it might look like this. So there is no elbow. However, if you have a data set where you see clearly such an elbow in the soft clustering error versus number of clusters, then it might be a good choice to use the elbow. Another option is if you use Gaussian mixture models as a pre-processing method, similar to k-means, we can also use the soft clustering algorithm as a pre-processing method, and then use the soft cluster assignments as input to some classification method like logistic regression. And then when you use then such a follow-up classification method, you do typically then compute the validation error. And the validation error is then something that indicates how good a choice for k is. So k is then something like a hyperparameter, and we can tune hyperparameters by trying out different values for the hyperparameter and then comparing based on the resulting validation errors. Okay, so to sum up today's lecture, the idea behind the soft clustering algorithm was to represent clusters by a Gaussian distribution. So you could think about using other distributions. So there might be other soft clustering algorithms that use other distributions than Gaussian distributions. However, maybe the most popular and most famous soft clustering algorithm that I know is based on using a Gaussian distribution, but it's a design choice in the end. Then I discuss the soft clustering algorithm, which turns out to be essentially fitting a Gaussian mixture model to data points by iteratively improving a choice for cluster means and cluster covariance matrices. And this interpretation as fitting a probabilistic model allows to define a soft clustering error via the logarithm of a probability. And using this soft clustering error, we can diagnose when the algorithm has converged or essentially converged, when there's not much progress anymore in the soft clustering error. However, similar to k-means, this soft clustering algorithm might get trapped in local minima, depending on the initialization and the data set. And to overcome this problem of local minima, we typically, or the standard use case is to run this soft clustering algorithm several times. And in each repetition, we use a different choice for the initial cluster means and covariance matrices. Okay, that's all from my side on soft clustering. Do you have any questions? You can now also ask questions related to other course aspects, please. In particular, regarding the project. There's one question, can I use clustering before linear regression in my project? Yes, you might use it, but it's not required. It's not mandatory that you use clustering in your project. Then another question, how to use this method in programming. So there is a nice library. I might also share my notebook that I used to create these images in my slides, but I might show you quickly what I like about Python or machine learning in Python, that you have a very decent help or user documentation. For example, so when I Google here a scikit-learn, which is the main library for machine learning, and soft clustering. So what I get is quite a lot. So here you even get an overview of many different clustering methods. So we talked about k-means. K-means is here. The implementation of k-means is quite easy, and you find demo code snippets in this online documentation. So you can just copy paste this and then insert your data set instead of the data set used here. So here's a synthetic data set used. And then there's also, of course, one for soft clustering, which is not called clustering, unfortunately, but Gaussian mixtures. So here, Gaussian mixtures. So let me show where this is implemented. Yeah, Gaussian mixture model. This is the soft clustering algorithm I talked about today, is this line of code. So one line of code implements this soft clustering algorithm. Okay. So then another question, I have done 2 models on my data, but my mean squared error is of the size 10 to the power of 10. Does a bad result in a bad grade, or does it depend on how you report and discuss it in a report? A very good question. So absolute numbers for errors don't matter at all for the grading. And if you receive grading from a peer that is bad because of the numbers, then you should report this feedback. This should not be taken into account. It's only about describing your process, how you implemented the methods and how you choose methods. It's the absolute values of errors or accuracies has no impact on your grading in the student projects, and you can rely on my word. Then there's another question. Could you please introduce some use cases in industry? One use case could be image processing or computer vision, where you want to do this background foreground segmentation, but with smooth boundaries. So this here, you want to segment the image, but you don't want a strict segmentation. So you want to highlight certain objects, make them brighter, so introduce visual effects. Another application is anything you would like to do with k-means, you might then also want to do with soft clustering, because soft clustering is just giving you more information. It's not only telling you this data point belongs to that cluster, it also tells you by which degree or how confident are we that this data point belongs to that cluster. So everything you want to do with k-means, you might also want to do with soft clustering, the soft clustering algorithm I talked about today. For example, outlier detection. Then another question, is there anything mandatory in the project besides having the training, validation, and test set error? Well, what is required in the project is precisely mentioned on the My Courses page. On the My Courses page, and we also have the reviewer questions there. So you see what the others will use to grade your project. So two methods, at least two methods. Train them on a training set, validate them on a validation set, then choose the better method based on the validation error, and then on the chosen method, compute the final test set error. That's basically about it. Then another question, can I report the accuracy on the training, validation, and validation set instead of errors? Yeah, so the accuracy in my view is just one specific choice for the loss function. So accuracy means 1 minus the average 0,1 loss. So instead of accuracy, you could use the average 0,1 loss, and this is also fine. So another question, so we have to do both, we have to implement both methods on training and validation set. Yeah, so you have two methods, like let's say linear regression, you want to use linear regression, and decision trees. You can train each of these models using the same training data set. And you can validate each of those two models on the same validation set, which must be different from the training set you have used before. Another question, is it normal that the test set has better accuracy than the validation and train accuracy? It can happen, yes. In particular, if you have very small data sets, there might be some statistical effects like artifacts when you have very small data sets. It's not written in stone that the test set performance is worse than the validation or training performance. There was one quiz question in the last round where actually the training error was always larger than the validation set because this was an unlucky data set. So it can happen. Then another question, if we need training, validation, and test set, does it mean I have to split my data set into 3 subsets? Yes. Any other questions? So yeah, the effect or the probability that the test set performance is better than the validation set performance is small in general, but the absolute number of data points you need, I cannot tell you, because this depends on how many features you use for the data points, and also I don't require you to analyze this any further. So you can just report it and mention. You could mention that it seems unusual, but it can happen that the test set performance is better than even the training set performance. There's no need to analyze this any further or consider this as an error or that something is wrong in your method. Not at all. Another question. Does it count as two models if I use k nearest neighbors with two different values of k? Yes, these are two different models. Another question, what is the ratio between train validation and test set? There is no general rule for this. You might use 50% for training set and 25 validation set and 25% test set. But basically you can choose any partitioning, because in this course we didn't study precise rules for choosing this ratio. It's up to you. But you should state it clearly. So in the project is more about training you or a drill to report precisely your process, how you implement machine learning methods. So if you need help regarding data imputation, yeah, please reach out to the TAs. They are happy to help. If you cannot get help from the TAs, you can also send an email to me, but there might be delays in my response time. Yeah, regarding data imputation, I highly recommend to check out the ready-made tools. So if you want, ask the question now. If it's a short question regarding data imputation, you can ask it now.